Hi, let's talk about the electric field. Now, when we learned about the force between charges, we talked about Coulomb's law and how the force depends on the amount of charge and the distance between the charges. But one of the questions that you might have is, how does the force actually get from one charge to the other? How does this charge over here know that the other one is exerting a force on it when they're not touching? And that is something that has always been a big issue for physicists. They talk about it as the force at a distance problem. One guy came up with a pretty clever solution, a guy by the name of Michael Faraday. And what Michael Faraday said was that each charge alters space around that charge. And if another charge occupies that altered space, it'll experience a force. And that altered space, we call that the electric field. And so the idea is that every charge has these lines of force that radiate out, and I'm going to make that go beyond, into space. And they radiate out in all directions and in 3 dimensions. And the idea is that the first charge, the one on the left, creates an electric field that the second charge experiences as a force. The force experienced by that second charge depends on the amount of charge of I'll call this the charge that experiences the force, or the charge in the field, and the strength of the electric field. And the strength of the electric field, if we rewrite that, is the amount of force per coulomb of charge. So in other words, an electric field strength of 1 Newton per coulomb, you can see that that would naturally have the units of newtons per coulomb, means that if I placed 1 coulomb of charge in that place, it would experience 1 Newton of force. If I had an electric field of 10 newtons per coulomb, then 1 coulomb would experience 10 newtons of force. If I know the field strength and I know how much charge I have, I can come up with the force. Now for point charges, the electric field strength has an equation that's going to look awfully familiar. It's KQ over R squared. Now if you notice, it looks almost identical to Coulomb's law, except for it's missing one of the charges. Well, if we think about the force as being QE, where this is in a sense the second charge, and this up here is the first charge, the one that's causing the electric field, then you can see that that really does turn into Coulomb's law, like so. But the electric field, what we're going to focus on is just this portion here. And that is how you calculate the electric field due to a single point charge. Again, it depends on the distance, inverse square, and the amount of charge. These field lines that I've drawn, a cool way of looking at these field lines is the further away from the charge you get, the more the lines spread out and the weaker the force. That's a cool way to think of it, and it actually works. So as you get closer, the lines get more bunched together and the force gets stronger. You might also think about how the fact is that these charges repel each other. So you say, well, how is it that this happens? Well, we know that if there's a force between 2 charges, they're equal and opposite. So if I drew the field lines of the second charge, whoops, that was supposed to change the color, but it didn't. There we go. This one's also making a field, something like that. Then that very first charge, the one on the left, is experiencing the field of the second charge. So they experience each other's field, and that's how they create these forces that cause them to repulse. And the direction of the force always follows the field lines. Now, if you had let's say a negative charge, which I'll draw down here on the bottom, the difference is the field lines, they still radiate out. Wow, that was terrible looking. Let's try that again. The field lines still radiate out, but the arrows point towards the charge, because a positive charge that was placed in this field would want to move towards the negative charge. So if you have to imagine what's going to happen by looking at these field lines, imagine what a positive charge would do. That's what the field lines tell you, is that a positive charge would move in a force towards this charge. A negative charge will behave exactly the opposite. Negative charges placed in this field will move in the opposite direction. So if I had a negative charge sitting out here, and the field lines are going towards this other negative charge, this guy would experience a force in the exact opposite direction. You can get combined electric fields that happen due to more than one charge. So for instance, if I had a positive charge here and a negative charge over here, well, you can imagine that if I placed a charge in between, it would be repulsed to the right by the left charge and attracted to the right by the minus charge, and the net effect would be a force that goes in that direction. It gets a little stranger as we get out here. We get something that starts to look a little bit more like this. Everywhere we see these lines, if we imagine where, let's say for instance, we had a positive charge and we placed it in this field, something like this, this positive charge would experience a force generally in the direction that the lines go. If you see a field and you want to estimate the direction of force, just make it follow the lines. Two positives make a slightly different looking field, because I can imagine that if I put a charge exactly between these two, it's repulsed by both, and you get this weird field that kind of looks like this, because charges that are positive placed between positive charges basically want to get out of Dodge. They don't want to be anywhere near these two positive charges, so they will kind of escape out and flee the scene. And so you just, get these cuckoo looking fields. And I'm not going to draw all the arrowheads because, my goodness, you guys don't have the patience for that, do you? Now let's do some calculation problems with these. Okay, we're going to do a problem where, first of all, we are going to find the direction and magnitude of the electric field at a place that's 2 centimeters away from a negative 25 microcoulomb charge that is separated from a 50 microcoulomb charge by 10 centimeters. In other words, we've got these two charges and we want to know what the electric field is right there. The electric field is a vector, so we have to determine the magnitude and direction. If you think about the direction due to the negative 25 microcoulomb charge, a positive charge would be attracted to that. So our first force will be to the left. Now the second force, which is due to the positive charge over here on the right, it'll be repulsed by that, and so it too will also be to the left. So once I find these two forces, I need to add them together. So let's start off with the first one. When I said forces, I really meant electric fields. So the first electric field, we'll call it E1, is K Q1 over R1 squared. And that's going to be 9 times 10 to the 9 times 25 times 10 to the negative 6 coulombs over 2 centimeters, which is 2 times 10 to the negative 2 meters squared. And that's going to come out to 5.63 times 10 to the 8 newtons per coulomb. Now for the second one, E2, brute, just kidding, K Q2 over R2 squared. And we'll have 9 times 10 to the 9. This charge is 50 times 10 to the negative 6 coulombs over 10 minus 2, aka 8 times 10 to the negative 2 meters, which then needs to be squared. And that's going to come out to 7.03 times 10 to the 7 newtons per coulomb. If we sum these, we're going to get that the total or net field will be the sum of those two numbers, which is 6.33 times 10 to the 8 newtons per coulomb to the right. An add-on to this might be, hey, what's the force on an electron? If I place an electron in that spot, what will be the force, magnitude, and direction for an electron? Now, again, the force is the charge that you place in the field times the field. Okay, we're talking about an electron. So we're looking at 1.6 times 10 to the negative 19 coulombs. The E field strength we just found was 6.33 times 10 to the 8 newtons per coulomb, and my force is going to come out to 1.01 times 10 to the negative 10 newtons. Now for the direction. The electric field is pointed to the right, but this is a negatively charged electron. That means that it will experience a force in the opposite direction of the field, so our force will be to the left. If you notice, this isn't a whole lot different than working with Coulomb's law, and it isn't. So if you mastered Coulomb's law, this should not be a huge problem for you.